All right, so we want to predict the emission wavelength that results when an electron goes from n equals 3 to n equals 2. And we're going to use the formula delta E is equal to Rydberg's constant times 1 over 1 nf squared minus 1 over n initial squared. Remember, this is also equal to hc over lambda. This is 2.179 times 10 to the minus 18 joules times 1 over 4 minus 1 over 9. 2 squared is 4, 3 squared is 9. I can get a common denominator on this. This will be 9 over 36 minus 4 over 36, which will be 5 over 36. And I'm just going to multiply that by 2.197 times 10 to the minus 18 joules. This is dimensionless, so my unit is going to be a joule. And when I simplify this, I get an answer of 3.026 times 10 to the minus 19 joules. Like I said before, this is equal to hc over lambda. Now, to isolate lambda, we can multiply both sides of this equation by lambda, and then divide both sides of the equation by what we just calculated for delta E. So a lot of times these numbers confuse people. Let's just go back to all variables. I'm going to multiply both sides by lambda, divide both sides by delta E. I'll get lambda equals hc over delta E. So we know that lambda is equal to hc over delta E. That's 6.63 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second divided by 3.026 times 10 to the minus 19 joules. And we can cancel out joules, and we can cancel out seconds, which gives us a unit of meters, which is good because that's what wavelength should be reported in, is in meters. So at the end of all of this, I get 6.569 times 10 to the minus 7 meters. That is 656.9 nanometers. And we were comparing this to the graph which showed it was at 655. That's a percent error of 1.9 divided by 655 times 100%. So I don't know what that is, but I know it's going to be good. That's a percent error of 0.29%. Excellent agreement with experiment.